All right, so we're gonna wrap up a little bit more on simulating risk, and then I'm gonna show you how to do some sensitivity analyses. And I think I heard some of you talking about assumptions, and so some of these maybe will be helpful for thinking about how sensitive your results are to different assumptions that your model may or may not be making. So if you want to follow along, you can find the slides here, bit.ly BEM 392 S22 slides 9. Okay, so going back to the rental scenario that we landed on Monday, someone's unmuted. Let me mute them. Oh, okay, good. I figured it out. So you're considering investing in a rental property. You've got the number of units is uniform between 20 and 30. R is the rent per unit. I've updated this from what we did last time. Now it's $450 per unit. And your monthly expenses are normally distributed with a mean of $10,000 and a standard deviation of $1,000. And the profit is going to be basically the number of units times the rent minus your monthly expenses. And so what I want you to do is go reopen that RStudio Cloud instance. If you just go to rstudio.cloud and log in, you should find the one that we were working on last time at the top. And I want you to write a function to simulate the profit for a rental opportunity with these parameters. So if you don't quite remember how to do that, you can either look back at your code from the last time, or if you want to go to our slides, you can find the slides from last time using that same short link, except instead of slides 9, it would be slides 8. And you can kind of copy those functions and edit them a little bit to match these parameters. So we're going to spend about 8 minutes with you doing it, and then we'll do it together. So try to write a function that can simulate under these parameters, run the simulation 1,000 times, and plot a histogram of the output, and then also try to calculate the chance of being profitable. I'm going to give you about 8 minutes to work on that, and then we'll do it together. How are y'all doing? Do you need time still, or you're good? Okay, well, let's start. I find finding the exact right timing is always a little bit tricky. All right, let me reload this and then we'll do it together. So I'm going to use the same code we did last time, but I'm just going to update some of the parameters. So now the number of units is uniform between 20 and 30. The rent is going to be $450 instead of $500, and the expenses is going to be $10,000 as the average, as opposed to $15,000. So I can take this same code that I had here, and actually I can take all of this, just copy it down to a new chunk. And I'm going to change this. So instead of a random uniform from 30 to 40, it's going to be 20 to 30. My rent now is $450, and I'm going to, my expenses have an average of $1,000. So I can run this and generate those simulations. And so now I can look and see kind of what my profit is. All right. And so if I make a little histogram, to make a histogram, I can take my Sims data and use the ggplot. X-axis is going to be profit. And now I'm going to use geom histogram to make a histogram. I'll use 30 bins. We can take a look at it. So this shows the distribution of the potential profit under these new parameters. I can draw a little vertical line here using geom v-line to draw a vertical line at 0 to show kind of the range where we would have no profit or even lose a little bit of money. And then I also can calculate the probability of having a profit. And so for that, I can take my Sims data and I'm going to summarize it. And I'm going to sum up the indicator that the profit is greater than 0. So profit greater than 0. And then I'm going to divide that by the total number of simulations, which in this case was 1,000. And so that tells me that 73% of the time I'm expected to be profitable, because 73% of the data kind of falls to the right-hand side of this distribution. I'm just going to stay here for just a second, and I'm going to show a couple different ways to calculate these type of metrics that are often of interest when we're thinking about risk. All right, so there's our rental scenario. Now let's say instead of the number of units being uniform between 0 and 20, let's say instead you want that to be actually input by the user. So now we're going to update our function so that it has one parameter u, and the user can put in the number of units they think that they are going to have. And this would let you sort of look at maybe a sensitivity analysis across multiple different u's. And so the things that have changed in this function versus what we had before is now I have one parameter u in my function call. I'm going to remove this line because I'm just going to have u be input by the user. And now because it's a user input, I'm going to output that in the data frame so that we can remember what the user put in, so we can compare it if the user puts in multiple values, for example. And so I've just removed that U line there because we're just having the user input it. What is the rent per unit in this scenario? Anybody? 450, yeah, so I'll put in 450. And then how do we generate from a random normal variable with a mean of, oh, this should say 1,000 and a standard deviation, 10,000 and a standard deviation of 1,000? Yeah, exactly. So our norm, we're going to just get one little variable, and we want it to have a mean of 10,000 and a standard deviation of 1,000. Very good. So the next thing is this is just some R code in case you haven't seen this before. I used this in class last time, but I didn't necessarily explicitly tell you what it was doing. There's this function called seq that it will sequence between a start and an end. So this is going to sequence from 20 to 30, and then you can indicate by how many you want to count by. So in this case, by 1, which outputs a vector that just has 20, 21, 22, 23, 24, up to 30. So this is sort of shorthand for being able to write out all these values. An even shorter way to do this, if you're going to be sequencing by 1, is you can just use the colon. So in R, if you put a starting number, colon, another number, it'll create a vector that jumps by 1 up into from the starting number to the top number. So I'm going to use this shorthand in the next part to be able to show you how we can look at different U values here. Okay, so now I'm going to rerun that simulate profit function 1,000 times. And I've used this little shorthand to indicate that I'm looking at rental values from 20 to, or I mean, number of units from 20 to 30. So basically, this is shorthand. Instead of writing out 20, 21, 22, 23, all the way up to 30, I'm just writing it like this. But behind the scenes, it's going to be the same thing. And so now what it's doing is I'm going to have basically 11,000 rows in this output, because it's going to run each of these 1,000 times. So it's going to look at what happens if we have 20 units 1,000 times, what happens if we have 21 units 1,000 times, all the way up to 30. So I want you to do the same update. Go ahead and update your previous function to allow for a parameter U instead of generating it from a uniform distribution. And then also update that function to output a data frame with 2 columns, profit and U. And then rerun this 1,000 times and vary U from 20 to 30 by 1. And then see if you can remember how to create a box plot to see how U impacts the risk. So this box plot is going to be similar to that one that I had made last class, where I basically used alpha on the x-axis and the return on the y-axis. In this case, your x-axis will be U, and the profit will be on the y-axis. All right, I'm going to copy this same code here. I'm going to make this a function of u and just get rid of this. I'm going to add one more line to my data frame so that I output that u. And now I want to look from 20 to 30. And so I've just updated my little simulate profit function to now be a function of the number of units. And I've also updated my data frame to include the number of units so that it comes out my output. And now I'm going to rerun this 1,000 times. And now I have this Sims object that has 11,000 observations. And I can see top of them, it has, for each of the U values, it has the profit associated for each of the runs. So if I wanted to make a box plot of this, I'm gonna use ggplot function again. What's gonna be on my x-axis? Yeah, factor u, and you want to make sure you use this factor function to turn this in, because if you don't, well, let's try it once without using the factor function so you can see how it goes wrong. So the y, what would be on the y-axis? Profit, yeah. And then what function allows me to make a box plot? Yeah, geom box plot. Okay, let's do this once just so you can see kind of how it can go wrong. So here you'll notice there was a continuous X aesthetic. Did you forget a group? And so it tried to just kind of treat this continuously. It didn't really know what to do with it, which is why we need to change this to factor, and that will treat it appropriately. All right, now this is a good start, but what if I wanted to actually include the data points to visualize them here? What would I do for that? Yeah, geom jitter. I'm going to set an alpha maybe to 0.1. Ooh, that's too much. Maybe 0.01. And then I'm going to remove these little outlier points with the outlier shape equals NA. And a couple more things to clean up this plot. For example, I might want to change the label on the bottom. I can use the labs function to change the label on the bottom to just number of units rented. Okay, so this gives me some sense. If I'm looking at this from a practical perspective, if I was trying to decide whether to make this investment, it gives me a good sense of kind of where I'd want to be in order to feel pretty confident that that this would be an okay investment. So for example, if I truly thought that I was only going to rent 20 units, the majority of this, the mass of this function here is below 0, which is not great. So that means if we only rented 20 units, we're basically, we're going to probably lose money with high likelihood. And so what I would do kind of looking at this sensitivity analysis here is I would assess kind of where I'd want to feel confident in order to feel like I can actually make this investment. And so if I'm looking at this, I'm going to say that like I probably want to be pretty sure that I can rent at least like 26 units before I'd be willing to make an investment like this. So this sort of gives you a visual depiction of the risk involved depending on this particular parameter, in this case, U. Here's another way to visualize this. There's a package in R called ggridges, and this I think is another kind of nice way to look at this. This basically looks at the distribution or the density of each of your simulations across the number of units rented. And so to do this, it's very similar to the code that I used for the box plot, except now I'm putting the number of units on the y-axis and I'm putting the profit on the x-axis. And this geom density ridges is what's creating these little ridge lines here, or these little densities for each of my different scenarios. And then I've incorporated a vertical line here at 0 to be able to denote kind of where I would be not profitable. And I've updated my label using that same labs function where I've updated the y-axis to be the number of units rented. And so I think this is another nice way to sort of be able to see the mass of the distribution. The box plot was okay, but with so many points, it was hard to sort of get a sense of where the majority of the points fell, with the exception of knowing exactly where the median and the interquartile ranges because that's how the box plot is drawn. And so this sort of gives you a better sense of the whole distribution of the data. And because in this particular case, the one thing that was random was the monthly expenses, and that was normally distributed, we would expect basically our estimated profits here to also look normally distributed. But if we had picked a different distribution to approximate how we think that our monthly expenses would be, then we would see a different shape here. And so that shape can be important when trying to sort of figure out the likelihood of different points. So I want you to go ahead and run install.packages ggridges once in the console, and that will install the ggridges package. And then using similar code to the previous slide, try to create a ridgeline plot of your sensitivity analysis. So of your simulations looking across the different values of U. All right, let's see. I'm gonna pull this code to install the ggridges package in our studio. And then I'm gonna use this code to be able to create these little ridgeline plots. Oops. So we want to first, we're gonna wanna use that library. So library ggridges. Oops, I spelled it wrong. There we go. And then we're gonna do ggplot. What am I gonna put on my x-axis? Profit. And how about the y-axis? Yeah, the number of units rented, exactly. And then I can use this geom density ridges. And oh dear, what didn't it like? What is it? Oh yeah, thank you. Nice. And then I can add a little vertical line. So I can use the GM vertical line to be able to put a line at the x-intercept to be able to show where we'd be not profitable or we'd be actually losing money. And I can update my labels here to number of units rented. Okay, so I think this gives kind of a little bit of a easier to look at picture in this particular case of our sensitivity analysis, looking how sensitive our result is or our probability of profitability is to the number of units that we've rented. And so what you all have done so far here is you have done Monte Carlo simulations to basically assess the risk of a particular choice or a particular investment or a particular kind of business decision. And you've also now incorporated the ability to look at sensitivity analyses where you can see how sensitive your estimates are to certain parameter inputs. And so in this case, we looked at how sensitive our risk estimates were to the number of units rented. So I think this is a really powerful tool because it's malleable. You can put in any estimate and it can help you make any decision as long as you kind of have some parameters for understanding the underlying mechanism of that decision. So when we're thinking about calculating risk, so far the one number that we calculated was your probability of being profitable. But there's a bunch of different types of numbers that you might be interested in. And so we're going to walk through a couple of those and you'll practice calculating them on this particular example. So the first thing is in all of these, when I say N, the capital N, I mean the total number of simulations that we're doing. So in the case of the exercises so far, we've always had that be 1,000, but just so you know what that is in the subsequent equations. So the one quantity of interest is the probability of loss. And so this is going to be in the numerator, it's going to be summing up from 1 to n. So from summing across all of your simulated values. I here means an indicator. So this is an indicator that your return or your profit is less than what your break-even point is. And so, for example, in the rental case, our break-even point was 0. So essentially not making a profit would be 0. And the return, the name of that variable in our data set was profit. And so we would sum up basically all the times that the profit was less than 0. And then you divide that by n, the total number of simulations that you did. So that's going to be your probability of loss. It's basically just how many times in our simulation did we lose money divided by the total number of simulations that we did. And so in R, you can do it like this. So here I've just simulated under one condition. So just when U equals 25. So I'm taking my same simulate profit function from before, but I'm just going to get one. I'm just going to do it under one instead of doing the sensitivity analysis. I'm going to bind those rows together. So Sims is going to have 1,000 rows here. And so if I wanted to calculate the probability of loss, I would take that data frame. I'm going to use the summarize function, which basically is a way to turn data frames into summary statistics. So I'm going to summarize across all my rows. And the thing I'm calculating is the probability of loss. And so this is my variable name, the probability of loss equals. And then this is going to be using that equation from the previous slide. So the way that we would do the numerator here was the sum where the return, which in this case is profit, is less than the break-even point, which in this case is 0. And so in R, if you put something like this, like this is a logical statement. And so it's going to check every row of this column profit. It's going to check whether it's less than 0. And if it is less than 0, it gets the value true, or equivalently the value 1. And if it's greater than 0, it gets the value false, or equivalently the value 0. And so if you sum up all of these, it's going to basically give you the total number of times in your simulation that your profit was less than 0. Does anybody have questions about how that part of the code works? we're going to be using logical statements like this to calculate a whole bunch of the different probabilities that we're interested in. Okay, so if this is my numerator, what am I going to put in my denominator here? Yes, exactly. It would be 1,000. And if I had changed this to 2,000, then this would change to 2,000, etc. So this is just the total number of simulations that you did. So when I run this code, I get 0.108. And so that implies that the probability of loss when you have 25 units is 0.108, or about a 10.8% chance of losing money. Okay, so what I want you to do now is run your rental simulation with U equals 22. So the 22 rental units, I want you to run that 1,000 times and then calculate the probability of loss using the function that we just went through. My little timer isn't working, but it's not like I actually obey the timer anyway, so I suppose this would be okay. All right, so I'm going to take this code here, and instead of looking at a range of U values, I'm just going to set it equal to 22. And if I want to calculate the probability of loss, what function will I use to create that summary statistic? Summarize, yep. You can use a Z or an S, some coder's choice. All right, and now if I want the probability of loss, what's going to be in my numerator? Yeah, so if I just run that, oops, seems to be Sims. If I just run that, I get a number, so 530. So that means that 530 times the profit was less than 0. And I can divide that now by the number of runs, 1,000, to get my probability. So now it's 0.53, which indicates that if I have 22 rental units, my probability of losing money is 53%. So that's pretty bad. It's not totally ideal. I don't think I would want to take this investment if I thought I was only going to get 22 rental units. All right, so we can also calculate the probability of profit, which is just going to be the inverse of the probability of loss. And so now in the numerator, instead of having the indicator be the return, that the indicator that the return is less than the break-even point, it's going to be the probability that the return is greater than the break-even point divided by the total number of simulations. And so in R, this top line was the probability of loss. What do you think the numerator will be for the probability of profit? Exactly, yes. So it's going to be the same thing, except it's going to change the direction of it. And similarly, we can get that by just doing 1 minus the probability of loss. And so the probability of profit here is also 1 minus the probability of loss. These will give us the same answer. And so in this case, when I was looking at 25, I had a 10% probability of loss and about a 90% probability of profit. Okay, so go ahead and spend a couple minutes calculating the probability of profit using the same method that we had used for probability of loss. And then we'll do it together. All right, let's do this together. So I can use this same, I don't have to rerun it. I can use that same output. And now if I want to add in the probability of profit, I can just do 1 minus the probability of loss, or I can use the equation summing up all the times when the profit was greater than 0 and divide by the total number of simulations. So I can call this profit 2, and you'll see that these two give us the same answer. So in this case, what this means is that if you have 22 rental units, you have a 47% chance of being profitable, assuming that the rent is $450 and your expenses are normally distributed with an average expense per month of $10,000 and a standard deviation of $1,000. Another common risk calculation is the expected loss. And so this is going to be your return times the indicator that your return is less than your break-even point. You would sum all of those up, and then you would divide that by the sum of the indicator that your return is less than your break-even point. So this is basically saying, assuming that we do lose money, how much are we expected to lose? So in kind of English words, as opposed to this math equation, all this is doing is it's taking all of that mass to the right side or to the left side of your kind of loss point, which in our case is 0. And it's taking the average value in that setting. So you're going to sum up your returns times the indicator that you don't break even, or that you make $0 or less. And then you sum up basically the total number of times that you make less than that. So in R, you can do this by taking the sum of the profit and then indexing. So what this is doing, the square brackets in R basically allow you to apply logical functions kind of to columns or to objects in R. And so in this case, what it does is it's saying we want to take only the rows of profit where profit is less than 0. So that's what this little piece of code here is doing. It's basically doing this top part here. It's return times the indicator that return is less than 0. Alternatively, I could have written this as profit times, and then in parentheses, profit less than 0. That would have given me the same answer. So there's kind of two different ways to do that part. And then we would divide by the sum of profit less than 0. So the total number of times that profit is less than 0. And so in this case, the expected loss is $522. And so this says that if we were to have 25 rental units, assuming we lose money, on average, we're going to lose about $500. And so you can see why, in addition to knowing your probability of loss, knowing your expected loss is also important. Because you could have a really high probability of loss. Like, let's say you had a 90% chance of loss, but you really were only going to lose about $1. Maybe you wouldn't be as worried about that. Versus you can have a very, very low expected loss, probability of loss. Maybe it's only 1%. But if you were to lose money, you on average are going to lose like $10,000. And that might also kind of play into your decision making about your risk. Okay, so go ahead and add in your expected loss into into your simulated data. I think thinking about risk is something that is really valuable and not always done properly. I think people don't always think about all the different facets of it, and I think from a business perspective, it has a lot of value. I'm a little bit biased. My husband his area is he works in risk for a financial institution, so this is like what he spends his whole life doing. So I suppose I think maybe I have an overvalued sense of its importance, but I do think it's his group, for example, he started just after the financial crisis, and if people had properly thought about risk, then a lot of that wouldn't have happened. So, and maybe then he wouldn't have a job. So I guess maybe in some sense, people doing it badly makes it good for people who know how to do it well. But it's an important concept, I think, to keep in mind when you're trying to make decisions. Okay, so I want to do the expected loss. I'm going to sum up the profit, and I'm going to do this a little bit differently than I had in the slides, just to show you how it can sort of exactly match what we had shown, what I'd shown in that equation. So I'm going to take the profit, and I'm going to multiply that by an indicator that the profit is less than 0. And so what this is going to do is basically, if the profit is greater than 0, then this just becomes 0, because this part here is 0, and multiplying something by 0 is 0. And if it's less than 0, then it takes the actual value. I'm going to sum that up, and then I'm going to divide that by the sum of profit less than 0. So basically, I'm dividing it by the indicator that profit is less than 0. And so here the expected loss is $861. And so not only do we have kind of a high probability of loss, you've got over a 50% chance of losing money. And if we end up losing money, we would expect on average we're going to lose about $861. So that's not ideal in this scenario. So just to show that this is going to be the same as how I had shown it with the brackets, I'll just redo this here. So instead of doing that multiplying, I can use this kind of shorthand in R, which is going to only select the profits where this condition is true, and this should give me the same answer. So it gives me that same 861. So these two are equivalent for calculating the expected loss. Okay, this one is super important, and I think the math looks a little funny, but it's very easy to calculate. So this is value at risk. Have you heard of these quantities in other classes before? No. Oh, good. Oh, I'm so excited to teach you something important. Okay, so value at risk is a very common, when you're doing any kind of like risk analysis, this is a common metric that people calculate. It's indexed at a certain alpha value or a certain percentile. And this basically just means it's the inverse cumulative distribution function at this particular point. But what that means is, in words, is that you have an alpha times 100 chance of losing this amount of money or more. So if you set alpha at 0.1, then you would have, so 0.1 times 100 would be 10. So if you set alpha at 0.1 and calculate this point, you would say you have a 10% chance of losing whatever this value ends up being or more. So this is a really, when you're trying to kind of decide on like how to allocate a portfolio, this is a really important number because often you want to know what that downside risk might be. So people typically set this at maybe 1% or 5% for kind of grounding values. And so the way you do this in practice is you find the alpha percentile of your simulated return. So this is going to be basically just finding the quantile of your simulated return, which is quite easy to do. So this equation, I think, looks a little bit daunting. This capital F just means that it's a cumulative distribution function, but in practice, it's quite easy to get this number. And so we use the quantile function in R to calculate a percentile. And so the value at risk for the alpha equals 0.01 or for a 1% risk is going to be like this. You'll just use the quantile function, plug in the name of the column that indicates your return. And the second argument is going to be which percentile you're interested in. So in this case, 0.01. And so here we get 1,058. So this means that you have a 1% chance. So assuming that you had rented 25 units, you have a 1% chance of losing $1,000 or more. And this or more is important because it's not, you could lose more than $1,000. It basically says you have a 1% chance of losing at least $1,000 or $1,000, $1,058.12. And so I could change if I wanted to know what the value at risk for 0.05 would be. I would just change that quantile to 0.05, and now it's 493. Can somebody tell me how you would interpret that number? Exactly. You have a 5% chance of losing at least $493 or losing $493 or more. And so using your rental simulation from the previous exercises, calculate the value at risk for alpha equals 0.1, so 10%, and alpha equals 0.01, so 1%. Give you a couple minutes to work on that, and then we'll do it together. Okay, if I want to calculate the value at risk for 0.1, what function do I use? Quantile. And then profit. And then what would my next argument be? 0.1. You know what? And if I want to do it for 0.01, what would I change? Yeah. Great. So now I've got my value at risk here, and this looks terrible. So this is saying if we have if we only rent 22 units, we've got a 1% chance of losing at least $1,400 or more, and or a 10% chance rather of losing at least $1,400 or more, and we've got a 1% chance of losing $2,400 or more. Yeah, so the value at risk is always going to be assuming that it's on the left side of your yeah. So yes, but you could, if you needed to, so I guess you could imagine a scenario, like let's say we know that if we set this to something bigger than 50.53, then it's going to be then it's going to be positive. So like, let's say 0.6, for example. You could interpret that as you have a 60% chance of making no more than $196. So either making $196 or less, or losing money, if that makes sense. So it's sort of, yes. Yeah. It depends a lot on like what the risk threshold for the individual is. So like in it, 1% is used a lot. That's a very common one, I think, just because it's like a benchmark. But sometimes people even start using like basis points, and so that would be like 0.01%. And it depends a little bit also on like your long-term goals. And so if you're doing an investment that you're going to hold for a long time, you might be more comfortable with a higher value at risk in the short term, because in the long term it might be, you can kind of ride out that potential wave, versus if it's a short-term investment, then you might be a little less comfortable with something like that. So I don't have a great answer for exactly what I think it is a little bit context specific, and also specific to the risk that the person or the institution that's kind of establishing it is willing to take. So I've been sort of framing this as like super negative for this particular case, but if you had, if we didn't think that the distribution, if we had changed these parameters such that rather than having the expenses being normally distributed, we had them like an exponential distribution or something that like basically there's a chance that you could actually make a really big profit, and there's kind of a small chance that you could lose a lot of money. So sort of having it more spread out, then these might not look so bad if you kind of were going to be making this investment consistently over like 30 years. Losing $2,400 1 year or 1 month might not be like so detrimental if you know that you would on average make a lot more in the long run. Does that kind of make sense? Yeah, it's a good question. Okay, so this is the last number that we're gonna do. It's the conditional value at risk. And so this is similar to that expected loss that we did before, except now the indicator is this indicator that you're on the kind of left side of whatever this percentile is here. And so this basically tells you that assuming that you're kind of in that tail area, what's the average return that you would have? And so in R, it's going to be just, now we're going to index based on that quantile instead of indexing based on the profit being less than some value. And similarly, the denominator is just going to be the profit, the indicator that the profit is less than whatever that quantile is. So the conditional value at risk at 5%, for example, would be this value. So this says, this is like a measure of the tail risk. It basically is a weighted average of the extreme losses. So what this tells us is that it's the expected loss if the worst case or 5% threshold is crossed. So assuming that we basically end up in our worst case scenario, on average, how much are we going to lose? And so you can go ahead and calculate the conditional value of risk at risk for these two alpha values. And then we'll do it together. And so just to tie it in with basically what we saw with expected loss, I'm going to copy this same code for expected loss here. And I'm going to change it to the conditional value at risk for 0.1, for example. And so now instead of multiplying by the indicator that profit is less than 0, it's going to be the indicator that profit is less than this quantile profit 0.1. Or equivalently, I could say that it's less than this var 0.1 that I already calculated. And then now in the denominator, instead of it being the indicator that profit is less than 0, it's going to be the profit is less than this value at risk. And so that tells us that's this number here, this 1900. And so that says if we do end up in the bad case scenario of being in the lower 10% of our tail, on average, we're going to lose $1,900. Oops. And similarly, I can copy the same code for the conditional value at risk at 0.1 or 1%. And now I would use the 0.1 index for that. And so this is saying if we end up in the bad 1% scenario, so we basically end up in that worst case, that scenario, we would on average lose about $2,700. So the conditional value at risk is always going to be worse than the value at risk because it's going to basically take the average of all of that area to the right or to the left of that distribution. And so this is saying basically if we were to lose if we were to be in this 1% scenario, we've got this 1% chance of losing $2,400 or more. And this says if we are in that 1% scenario or worse, on average, we're going to lose $2,700. So often when people are trying to make like investment decisions or other kinds of decisions in general that have kind of numeric values associated with them, the conditional value at risk is going to be if you're being a little bit more conservative and want to really understand your tail area risk. That's what people will calculate. Okay. So now we can turn this whole thing into the sensitivity analysis. And so what I've done here is I now, instead of just doing it for a single U, so before I was looking at 25, and in your example, you were looking at 22, I've gone back to the sensitivity analysis where we look at a range of values. And now we can calculate all of these same probabilities, but grouped by this U. So I can see how these different values, these different risk calculations change depending on the number of units. And so this group by that I put at the top will basically say that it's going to calculate these summary functions within each U group. And so this is what that looks like here. So I simulated the profit from 20 to 30, and now I ran the probability of loss. And I can look at what that probability is across all these units as a single summary measure. And so by looking at this, I can see like if I get at least 26 units rented, I have about a 5% probability of loss. And so maybe I would use this information to say that if I can feel very confident that I would have at least 26 units rented, then I would take this investment. And if I were not as confident of that, if I thought that there was a high probability that I could have only 20 units rented, then maybe I would choose not to make this particular investment. So I am going to, instead of, just in the interest of time, I'm just going to show you how you can basically, if you take that exact same code that we've done before, I'm going to change my U here to 20 to 30 and just add this group by U. And now I can calculate this exact same quantity for every value of U. And so the group by function lets me calculate these summary statistics within each of the U categories. And so now I have my probability of loss, my probability of profit, my value at risk, and my conditional value at risk for each of these different scenarios. And you'll notice here, like what Noah was asking about, when you have these positive numbers, kind of what those end up meaning is essentially the whole quantity is like, what is the probability of being at this point or less? And so in this case, it would be like, what is the probability? We've got a 1% probability of making $741 or less. And that or less includes making less than $0, so losing some money along the way. Are there any questions about that? Okay. Okay, so now I'm going to move on to another type of sensitivity analysis that might be useful for your projects. This is the sensitivity analyses for regression models. And so I've got 3 examples here for when you might do something like this. And we're going to use kind of the same types of tools that what we've been doing for risk analysis. We're going to simulate or kind of plug in certain values for our missing data and see how that changes our result. Or rather than simulating, we might just run our models in different ways and see if our ultimate result of interest changes when we've varied our models. So for missing data, the best case scenario is something like multiple imputation. Well, the best case is you have no missing data. And the second best case, if you have missing data, is to do something sophisticated like multiple imputation, which I know some of you are going to be doing for your project. And so this multiple imputation basically takes the information that you have in your data frame and it tries to guess what the missing values would be. And so this is going to be correct if you have measured all of the things that dictate why someone might have a missing value. But even it's possible that even this could lead to the wrong answer if you kind of are missing some quantity that predicts what someone's true value would be. And so you could even find yourself doing some simulation or some sensitivity analyses, even if you're also doing multiple imputation. But in the absence of that, the sensitivity analyses that you would do would be something like this. So first, you might just do a complete case analysis. So you would do an analysis where you remove all the missing data. And then you might do a second analysis where you replace all the missing values with the average value. And then a third analysis, maybe you would replace all the missing values with an extreme value. And this one is this kind of picking the right extreme value here is going to be what's going to sort of drive your sensitivity analysis. And so you could pick different values for all of your missing data and basically see how it might change your result. So ultimately, if all of those 3 analyses reveal similar results, then your analysis is robust. And so you would often, if you're doing this in practice for a client, you would really only show them one of your analyses. If all of them give the same answer, it doesn't really matter which one you choose to show them. So often if I'm doing this, I show them the one that's the simplest to explain. And then in like an appendix somewhere, maybe I would include that we checked all these sensitivity analyses and they all sort of yielded the same result. So this is kind of the practical way. A lot of times we hear about all these types of assumptions that you need to have met in regression analysis. But it's not always the case that those assumptions being violated really changes our ultimate result. And so sort of being able to test whether or not that happens before you start investigating more complex methods is often kind of a practical approach to this. Another really common one is nonlinear data. So the best case scenario is that you know the true functional form of all of your variables in your model, and you include that functional form or transformations of your variables appropriately. But sometimes that's not possible. Sometimes it's not possible because you don't know the functional form, or sometimes it's not possible because you really don't have enough data to estimate accurately like a wiggly line. So if you don't have enough data to do that, you can end up basically overfitting, which is also not ideal. So in this case, what you can do this, use the same kind of tools to conduct a sensitivity analysis. And so in that case, the analysis 1 would maybe fit the variable linearly, like just including the variable kind of as itself in the linear model. Analysis 2 might fit the variable with polynomial terms. So polynomial terms is like if the variable was x, a polynomial term would be like x squared, x cubed, x to the 4th, etc. So you might fit a model where those variables that look like they have a little wiggle in them, when you look at the plot, you might add some polynomial terms. Or analysis 3 would be fitting the variable with a natural spline. And so a natural spline is basically an improvement on analysis 2 in that it essentially fits a polynomial, a cubic polynomial between certain knots, which are dictated by the like distribution or the percentiles of the data. It's not, for this particular class, it's not super important. Some of you, if you've taken like a 363, the machine learning or statistical learning class with me, you would have learned the mechanics behind natural splines. And I think that we don't really have time to get into the mechanics in this class, but just to sort of know that this is an option if you have data that is nonlinear, it's a nice way to be able to fit that data in a model without having to actually specify the number of polynomial terms itself, since it just fits these cubic functions between pre-specified knots. Okay, so here's how I would do this in R. So sensitivity analysis for nonlinearity. The assumption here is that I'm fitting a linear model. I'm trying to predict miles per gallon. And I've got 3 variables in my model. I've got this CYL, DISP, and WT for weight. And the variable that I'm worried about is this WT, or this weight variable. And ultimately, the thing that I'm interested in are the predicted values. So I'm taking my linear model and I'm using this predict function to get the predicted values out of it. And so the thing that I'm trying to give my client are these predicted values. My goal is prediction here. So analysis 1, I just include weight as linearly in the model, so just as itself. Analysis 2, I include it with a 3rd degree polynomial. So this poly function in R basically creates those polynomial terms for you. And so by using poly with the 3 as my argument, it's going to input weight squared, and weight cubed into my model. So this kind of gives you this little wiggly term to account for the potential nonlinearity of weight. So I'm going to do that same thing and get those predicted values. Oops. And then analysis 3, I'm going to fit a natural spline. So there's a package that comes in base R called splines. And there's a function within that package called NS, which stands for natural splines. And so what this is doing is it's fitting a natural spline to that weight variable. And 3 here indicates that I'm dedicating 3 degrees of freedom to this spline. And then I'm getting those predicted values as well. And so for this sensitivity analysis, basically I'm going to compare P to P2 and P3. And if they look really different, then maybe I'd make some choice about whether or not I'm going to include some kind of nonlinear term for weight. But if they look exactly the same, then I probably will just use my linear one, since that's the easiest one to explain to my client. And so there's a couple different ways you can look at this. I chose first to look at it via a box plot. So I put those 3 values, P, P2, and P3 into a data frame. And I made a column called linear, polynomial, or spline to indicate which analysis it came from. And I saw here that I end up with it looks like they kind of all always come up with the same average value here. So there doesn't look like there's a big difference between the linear, polynomial, and spline versions. Another way to do this would be to look at the difference between those predicted values. And so here again, I made my data frame and I mutated to create a variable called diff that looks at the difference between my predicted value if I just had a linear term for weight and my predicted value if I had a polynomial term for weight. And I just plotted these points here. I put a little line here at 0. So this, if they were exactly the same, they'd be 0. And this kind of lets me look at that range of difference. And so what this shows me is that I was always basically within 3 or so, there's one point a little over 3, but I basically tend to be within 3 miles per gallon of my predicted value, regardless of if I use a linear model or a polynomial model. And so depending on the precision that your client is interested in, that might be sufficient. So the range of miles per gallon here, it was sort of, I think if I looked at it, it looked like it was like 18, 19, 21. Those were kind of the common values that you saw. And so if someone was really interested in precisely estimating the miles per gallon within 3 miles, so if like 21 is really different than 19 or than 18, then maybe I would want to sort of think about whether or not I'm including a nonlinear term. But if your client just wanted like a rough sort of estimate of miles per gallon, then maybe this would be fine to just include as a linear term. And I did the same thing with the spline, and I saw kind of pretty similarly that we were always within about 3 miles per gallon in terms of the prediction. But does that make sense to everyone? Sort of how you would do these types of sensitivity analyses? Okay. The last one is for outliers. So this is another very common thing that we always teach when we're starting any kind of regression analysis class, we usually talk a lot about outliers. The best case for an outlier is that you understand the mechanism for the outlier. So if it's a data error, then you would remove it. But if it's a true value, then you would choose to keep it. And so for sensitivity analysis, this is pretty straightforward, but basically you're going to fit your model with the outlier and then fit your model without the outlier and see how that changes your result. And so I have an example here that I was going to have you all go through, but we only have 3 minutes. And so I'm going to do it. I'll code it up and you can sort of code along with me if you'd like. But essentially, I'm using this Star Wars data set, and I'm interested in the relationship between height and mass after controlling for species. And so first we can create a scatter plot of height and mass and check if there's any outliers. And then I'm going to use the Star Wars data set to fit that linear model and look at the beta coefficient for mass. And then I'll filter out any outliers and refit our model and see how that changes our result. And so this kind of gives some sense for sort of how you would do a sensitivity analysis like this. And so we're going to start with fitting, creating that ggplot of the Star Wars data. So Star Wars, this data set comes in the tidyverse package. I'm going to plot mass on the x-axis, height on the y-axis, and I'm just going to look at some heights here. And so you'll notice we've got this one outlier way out here that's got kind of medium height, but a really big mass. So this is Jabba the Hutt. That's why he's out here. And so I'm going to see how much that influences my ultimate model. I'm going to make a linear model. I'm predicting height using mass and species. So basically what this model is telling me is controlling for species, how much does mass change? How much can we predict mass? How much can mass predict height? Okay, so I run this model and I get my beta coefficient for mass is 0.6769. I'm just going to write this here so I can remember it, 0.6769. So that tells me that a 1 unit increase in mass yields a 0.6769 increase in height, holding species constant. All right, now let's try to filter out the outlier to see if that changes our results. So here I'm going to filter. I'm only going to include data where mass is less than 1,000. Since when I looked at this point, the only one that was greater than 1,000 was this outlier here. I'm going to filter where mass is less than 1,000, and then I'm going to fit that same linear model that I fit before, except now the data is going to be, I'm going to use the dot to indicate that I want to put this filtered data set into that data argument. And so when I run that, I get the exact same mass. It's still 0.6796. And so basically, regardless if we removed that outlier, we ended up with the exact same beta coefficient. And the reason that happens in this particular case is because we accounted for the thing that made that value an outlier was the species. And we accounted for the species in our model. And so because we had accounted for species, it didn't matter that we had this outlier. And so this is like an important kind of, when you're thinking about these different, when you're thinking about assumptions, being able to actually test how much those assumptions influence your ultimate result is the like big picture that you're often trying to do anyways for any client. Okay, so hopefully that is helpful.